Alright, I'm going to talk about D3 again a little bit, like we did in class today, and I just wanted to rewrite the notes before I did so. So remember that we have 6 total elements that live inside of D3. The first one is going to be just our identity element, and that's going to do nothing to that triangle. And we're going to call that thing R sub 0. So we're starting with this triangle on the left here, and it's turning it into the one on the right there. Secondly, we can have a rotation of 120 degrees. And so we'll call that thing R sub 120. And again, that's counterclockwise. We can have a rotation of 240 degrees, which is this thing. And so we'll call that R sub 240. If we did 360, we'd wind up back at R sub 0, because that's just like doing nothing. And then we have the reflections. So one reflection is if we were to hold that 2 to be fixed and reflected it over this line right here. And so it becomes this thing. The second one, we could hold that 1 fixed. It's going to become this if we rotate 2 and 3. Reflect 2 and 3. And then lastly, if we were to hold that 3 fixed and 1 and 2 are going to flip. And so that's the last one there. Okay, so for the second one, we had this rotation, this reflection. And we had this for the third. So we'll call this V, D1, and D2, diagonal 1 and diagonal 2. And so the dihedral 3 group, D3, is going to be made up of those 6 elements: the identity, R sub 0, R sub 120, R sub 240, V, D1, and D2. Alright, so if we were to look at a Cayley table for this thing, meaning the operation table, we get this thing. So what this means is, if we take, let's say, R240, and then we compose it with, let's say, V, then we're going to get D2. And notice that it has closure. These are associative, and each of these is going to have an identity and an inverse. So we want to take a look at everything that we possibly can with this group to kind of fully understand it, because we don't really understand what's happening with it just yet. And we do that by looking at what we call the group representation. And we know that if we take 2 elements inside of this thing and we do a bunch of operations with them, then we can come up with pretty much the whole group. Alright, so when we do that, those elements that we chose are called generators. So we're going to choose some A that lives inside of this set, some B that lives inside of this set. So A is going to be one of these, B is going to be one of these, but we don't know which is which. And when we do that, A and B, if we put them together with a bunch of operations, they're going to be able to build the entire set. That's why they're called generators. So we have to figure out which of the elements are going to be, well, which of all of them will be B and which of all of them will be A. So it's pretty easy for us to do because we have this group presentation, we call it, and we can say that D3 is going to be created by two elements inside of that group, A and B, such that A cubed is equal to B squared is equal to the identity E, and AB is equal to BA inverse. So with this, we should be able to choose from those 6 elements, and one for A, one for B, and figure out which of them are going to match this. So right here, this thing says that the order of A is 3, meaning if I cube A, it's going to give me the identity E. And we can see right away that R sub 120 is going to do that. If I compose it with itself, I'm going to get R240. And then if I do it one more time, I'm going to get back to R sub 0. And that means that we're back at the identity. That means that we cubed it, and we ended up at E. So let's just go ahead and maybe conjecture that A is going to be 120. And we know that whatever B is, when we square it, we get E. Well, that could be V, because if I flip something and then flip it again, it's going to go back to the identity. It could also be D1 or D2. But what's important here is this thing over here. A times B is going to be B times A inverse. And it turns out that it's going to be B is equal to V. And so we want to check that A times B is equal to B times A inverse. All right, so we want to test what we chose A and B to be to see if they're actually going to work. So we'll do that. So A times B is the same as saying R120 times V. Now we know that R120 times V is going to give us D1. Now we have to think about what the inverse of A is. So the inverse of A, what's going to get A back to the identity? Well, it's going to be R240. So A inverse we know is going to be R240. And so if we do B times A inverse, that's the same thing as V times R240. And we end up with D1 again. And so AB is equal to B times A inverse. Okay, so it works. So what this tells us is that when we found D3, which we knew was R sub 0, R sub 120, R sub 240, V, D1, and D2 to be generated by these generators A and B, we can now write the set as E, the identity, A, B, A squared, A times B, and A squared B. And so this Cayley table that we've seen before, we can actually rewrite it now just simply in terms of those elements. These two things are exactly the same. It's just that we're writing this D3 that we already know in terms of the generating elements A and B right here. And we can do that for any D sub n, which is the set of symmetries of any n-gon. And so we do that by saying we would have some A cubed is equal to E. We would have some B that is raised to the n, and that would give us E. And then we have this A times B that we would square, and that would give us E.